This simulation will be focusing the performance and characteristic of permanent magnet DC motor. So the objectives of the simulation is to record the characteristic of a permanent magnet DC motor under varying load. Secondly, to calculate the efficiency of a permanent magnet DC motor. So all DC machines, to be particular, the DC motors, so they can be visualized using the Fleming's left-hand rule. So that is the principle of a DC motor is that when a current carrying conductor passes through a magnetic field, so the conductor will experience a force that is perpendicular both to the conductor and the magnetic field. So the relationship between the force, the current, and the magnetic field is given by the left-hand rule as proposed by Fleming. So the thumb represents the direction of the force, the pointing finger represents the magnetic field, and then the middle finger represents the direction of the current. Now, since we are studying the permanent magnet DC motor, we expect the source of the magnetism to be coming from, of course, a permanent magnet. So it means that there is no way for the DC machine or DC motor to vary the strength of the magnetism, because unlike with the electromagnet that the strength of the magnetism can be varied by varying the current flowing into the coil, in a permanent magnet the strength of the magnetism is fixed or constant. So any machine or any uh, machine or DC machine, when given with a voltage, okay, so together with the utilization of magnetism, the DC machine will develop what we so called torque. The DC machine that converts electrical into mechanical energy is termed as DC motor. So this will be the circuit diagram of a permanent magnet DC motor. Okay, so as you can see the field. Okay, so this one is not supplied with an external voltage source, only the armature. Okay, so the armature is being supplied with the source voltage. So what happens is that when the voltage is given to the terminals of the armature, so current will flow to the armature winding. Okay, so and based on the principle stated by Fleming, okay, so when a conductor, so the conductor or conductors are present in the armature winding, so when current flows into the conductor and then there is a source of magnetism, so each of the conductors in the armature will develop force. Okay, so now this force is actually being utilized to move or to make the armature rotate. So assuming that this is the permanent magnet, okay, so we have there the North Pole and the South Pole. So the magnetism will, okay, so by convention will run from the North Pole going to the South Pole. So this should be represented by the symbol flux or magnetic flux. Now each of the conductors in the armature, okay, so each of the conductors in the armature, okay, so represented by the blue one. So when current passes through, okay, so these conductors, okay, so this current IL will pass through. So to the conductors going to the negative terminal of the DC source. So according to Fleming, when that conductor is exposed in a magnetic field, each of the conductor will develop force. Okay, so the force is perpendicular to both the field and the conductor itself. So this would be the forces or the force that the conductor may experience. So through this force, okay, so since the armature is mounted symmetrically, so this force will in turn develop torque, and which actually makes the armature of the motor rotate. Okay, so now we will be simulating the performance and the characteristic of a permanent magnet motor using multi-sim. So again, we let the load of the permanent magnet motor to be the generator. Okay, so and then we try to vary the load case at the generator, and we will be observing the effect of the varying load of the generator, okay, so with respect to the output of the permanent magnet motor. So we will be observing the torque, the speed, okay, so the current drawn by the permanent magnet motor as the load in the generator increases. So the meter XMM3 represents the voltmeter to measure the voltage. Okay, so across the generator terminals, meter XMM4 represents the ammeter. So used to measure the current being drawn by the permanent magnet DC motor. So the source voltage is 100 volts. Okay, so kindly take into consideration the format of the field resistance in the generator, so which is R2. So for us to have the same results, so kindly follow the positioning of the field resistance R2 to set it to 30%. So field voltage is set also to 100. Okay, and then the machine parameters for the, okay, so the DC generator would be this one. Okay, so let's check that later during the simulation process. Okay, so and then this would be the table that we need to fill up. So the motor supply voltage should be constant at 100 volts. Okay, so the speed, torque will be measured. So power output will be calculated, and lastly, so the efficiency of the machine will be calculated also. So this should be the setup for the uh, permanent magnet motor coupled with the generator. Okay, so to insert the permanent magnet motor, this one, okay, so you go to this button, so place electromechanical. Okay, so you may click this one and click machines, and then click DC machine permanent magnet type. So after which you can press OK and then close. Okay, so you will have this one. Okay, so connect it the same process as what you've done in the previous experiments. Then couple the shaft of the motor to the shaft of the DC generator. Okay, so this one. So for the DC generator, we'll try to see if, okay, so the parameters are the same as with the given. Okay, so you have there 0.1, 0.2, 0.2, 500. Okay, so they are the same. Okay, so the lamp. Okay, so the maximum rated voltage. Okay, so for the lamp is set to be or set to 250. Then we'll try to vary the uh, rated power of the lamp. Okay, so and observe what will happen to the output of the DC motor. Okay, so for the DC motor, okay, so kindly follow the given specs. Okay, so armature inductance 0.1, armature resistance 0.2, speed constant, torque constant, and so on. Okay, so you try to change or you change the parameters, okay, so of the permanent magnet motor before doing the simulation. Okay, so click OK, and then to measure the torque, okay, so use this voltage button. Okay, so put it there. You may adjust the reading. Okay, so reading interface, and then for the torque, you can use the ammeter and adjust the reading interface of the output torque. Okay, so we'll try to go to the table. Okay, so this one, then we go to the results, data and results. Okay, so okay. So again, do not forget to follow the positioning of R2. Set it to 30%. Okay, then set ammeter. or XMM4 or this meter to ammeter setting. Okay, so and then we're now ready for the simulation process. So the DC generator load is initially 0. So that means we have to disconnect the load first. Okay, so this would be 0. Then we'll run the simulation. You may press this button or F5 button in your calculator, I mean your computer. Okay, so to directly run the simulation, so click this one. Okay, so and then okay, so you notice that uh, when the okay, so when the motor is driving the generator at no load, so the terminal voltage is 142.814. The current flowing or the current drawn by the permanent magnet motor is 79.988. So we can make this one 80 milliampere, and then the torque is 2.0 milli. Okay, so this would be in terms of milli Newton meter, and the speed, that's 2.0 kilo radian per second. So we'll try to record. Okay, so the following details. Okay, so we have there 100 volts. Okay, so motor line current is 80 milli. So that's okay. So that's 80 milli. Eighty times 10 to the power of negative 3. So the input power can be calculated by multiplying the voltage and current. So multiplying the voltage and current will give us 8. So the speed in radian per second is set to 2000. Okay, so that's radian per second. So the torque is 2 milli. Okay, so you may omit. So by the way, the so units. Okay, so we have already the units given in the header of the table. So the torque is 2 milli. So that's okay. So 2 milli, it's 2 times 10 to the power of negative 3 Newton meter. So to calculate the output, so we use the formula 2 pi nt over 60, but you have to convert. Okay, so the speed in radian per second to revolutions per minute. So you can do that by multiplying the radian per second. Okay, so by 30 over pi. So that's 2 pi nt over 60. But then again, n must be in revolutions per minute, so you have to multiply uh, the speed in radian per second by 30 over pi. Okay, so calculating the power output of the DC motor, so you have there 2 pi. Okay, so times, okay, that's torque, okay, negative 360. So the answer is 4 watts. So the efficiency can be calculated by dividing the power output. Okay, so dividing the power output over the power input and multiplying it with 100. So we have there 50%. Okay, so now next is to increase the load of the generator. So okay, you stop the simulation first. Okay, then change this one to 25 watts. Okay, then okay, connect this one is to the terminals of the generator and then run the simulation. So wait until the reading of the meters, okay, so to be stabilized, and then record the data. Okay, so you notice that the speed remains constant, the torque, okay, so the output torque increases, okay, so and the current also drawn by the DC motor also increases. Okay, so let's try to record. Okay, so the source voltage should be 100. So the motor current is, okay, so set to 161.55 milliampere. Okay, so that's, so 161.55 milli. Okay, so such that the input, okay, so that's 100 times 161.55, that's 16.16. Okay, so the speed remains the same, 2000. The torque, as you can see, the torque increases. Okay, so that is because the load of the motor starts to increase. 6.08 times 10 to the power of negative 3 millinewton meter. So the output can be calculated. Okay, so using the same formula, that's 2 pi nt. 2 pi times the speed, okay, so times 6.08 negative. So that's 12.16 watts. So the efficiency would be, okay, divided by 16.16 times 100. That's 75.25. Okay, so the same thing. Okay, so you have to continue the gathering of the results. So starting from 50 watts up to the 200 watts generator load, and then in your final report you'll be analyzing the performance, okay, so of the, okay, so the permanent magnet motor. Okay, so you may have the supply voltage to be fixed at 100, while the other data may or may not vary. So you use the software to simulate, and then later on, so do the graphing of the characteristic of the permanent magnet DC motor.